We conclude this chapter with one example of how we might apply what we've learned to a design problem, and then some extensions of the root locus plotting rules that can also be helpful in certain situations. So first, the design example. We see here we have a unity feedback system where we have a compensator gain K that we want to design, but notice also that we are considering to have a 1 over S plus A as part of our compensator, where A is a design parameter. So what we haven't considered before is what happens to the root locus if two things are changing, in this case K and the value of A as well. This here is our plant. It's S plus 1 over S squared. But for the purpose of the root locus, what we're going to do is say, well, the root locus rules allow us to plot versus this variable parameter K what happens to these combined dynamics here, which when I put together is going to be 1 times S plus 1 all over S plus A times S squared, which is this G of S. So the root locus rules apply when I am selecting or varying one parameter only. It doesn't apply if I'm doing two things at once, like I might want to do here. I might want to vary both A and K simultaneously to see what the combined effect is. So in order to get around that, what we're going to have to do is we're going to have to select representative values of one variable and then plot the root locus as a function of the other variable. And what we choose to do here is to select 3 different values of A and see how that impacts the root locus when then I plot the root locus as normally as K varies from 0 to infinity. So we're going to choose, see what happens when A equals 2, A equals 50, and A equals 9. So to plot the root locus, the first thing that we do is we put down where all the poles and the zeros are. And I've got a 0 we see at -1. And I've got 2 poles at S equals 0, so I've got 2 poles right there. And I've got some poles elsewhere. Excuse me one second, apologies. So I have poles then at A equals 2. So the pole is at S equals -2. That's one candidate location. S equals -9 is 2, 3, 4, 5, 6, 7, 8, 9 is over here is another candidate location. Then S equals -50 way over here is a third candidate location. And I kind of can't draw that very easily to scale. When I'm looking at the root locus, first thing I do is I plot where it exists on the real axis. And so I take my test point and I move it. I'm to the left of 0 things, 0 things, 0 things. Now I'm to the left of 2 things, which is still even. Finally, I'm to the left of 1 thing. And so I plot between the 0 and the pole, whether the pole is there or there or there. That is where the locus exists on the real axis. Next thing I do is I consider asymptotes. First, how many are there? So n equals number of poles is going to be 3. M equals 1. So n minus m equals 2. There will be 2 asymptotes, and they will go to plus minus infinity at plus and minus 90 degrees. But centered where? Well, I take alpha, which is the sum of the open loop poles minus the sum of the open loop zeros divided by 2. Well, open loop poles, I've got one pole at 0, one pole at 0, and another pole at minus A. And open loop zeros, I've got one at minus 1. And so when I take negative A minus minus 1, I have 1 minus A, then divide by 2. So this is my alpha location. So if A equals 2, I have minus 1/2. If A equals 9, I've got minus 4. If A equals 50, I've got minus 24.5. So my possible locations for asymptotes, minus 1/2, minus 1, 2, 3, 4, or way over here somewhere minus 24.5. Those are where I'm going to go to plus minus infinity along those lines. And we know that the angles are 90 degrees. Okay, what about departure angles? We know that this pole is going to depart and go that way, and this pole is going to depart and go that way, and that pole is going to depart and go that way, just simply from the real axis rule. So that the departure angles from those poles are going to be 0 degrees. But what about the departure angles for the poles at the origin? That's kind of interesting. So we have a multiplicity there of two poles at the same place. So 2 times phi departure equals the angle from all the zeros minus the angles from the remaining poles minus 180. Notice that the angle from the 0 is 0 degrees because it's pointing straight right from the 0 to the poles. The angle from all the other poles is just that one pole at minus a, which is also 0 degrees. And so I'm going to have that the angle from the zeros is 0, the angle from the remaining poles is 0. So phi departure is going to be minus 180 divided by 2 from there, minus 360 divided by 2. So that's going to give me plus minus 90 degrees. So those two poles are going to go straight up and straight down originally. They are going to curve toward those asymptotes, we know, but it's going to start out by going straight up and straight down. We could do the Routh test. We'll find out that for positive k, the system is always stable, so there's no imaginary axis crossings. In fact, the only imaginary axis crossing is right at k equals 0, where the two poles are together at s equals 0. We can also look for breakaway points to see if there's intersections anywhere with this locus. And so what we have then is we have k of s is minus 1 over g of s is there. And we take the derivative of k of s with respect to s. And again, it's going to be the denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared equal to 0. And we work all of that out, and we get that we have this equation equals 0. This tells us that we have a breakaway point when s equals 0, where two branches of the locus intersect, and we know that because I have at s equals 0, I've got these multiple poles right there that have come together and are actually splitting apart from there as k increases above 0. But then I also have this quadratic, and if I solve for the roots of that quadratic, it's also possible to find these breakaway points. So let's look at that. Solving the quadratic, I have, this is my quadratic A, my quadratic B, my quadratic C. So I have minus B plus or minus B squared minus 4AC over 2A. And there should be parentheses around that. And solving for that, putting in different values of A, these are the values we get for the roots when the value of A is equal to 2 or 50 or 9. So when A equals 2, these are the solutions, but we can plug that back into the equation and find out that 1 plus kg of s is not equal to 0. So in fact, that value of s is not on the root locus. It's an extraneous point. So when A equals 2, there are in fact no breakaways on this root locus except for the one at s equals 0. However, when k equals 50, I do have two breakaway points. I've got one at minus 2-ish and one at minus 24.4-ish, which is interesting. And when k equals 9, I've got one at negative 3. So let's think about this. What do I have? I have When A equals 2, I've got these two poles at the origin. One starts out going straight up and straight down. The real axis rule tells me that this is part of the root locus right there. And the asymptote rule says I eventually get something going across the asymptote toward plus minus infinity. And I know that there are no additional breakaway points, so I can sketch in the locus like that. When A equals 9, we again have these two poles starting going straight up and straight down. I know from the real axis rule that that portion is on the root locus. I know eventually I have roots going straight up and straight down, but I also know that at minus 3 I've got a breakaway point. So I've got a minus 1, 2, 3. I've got a point right there. Well, this is really fascinating. If we hadn't solved for the breakaway points, we would be tempted to think that the root locus looked a lot like what happens when A equals 2. But because we did solve for the breakaway points, we know that can't be true. So what happens here is interesting. You can kind of scratch your head on this for a while and say, well, how can this be? I have to have two poles going up and down, and this one has to be going that way, and something has to end up at that 0. How can I have a breakaway point there? Well, what happens is that, in fact, I've got a multiple breakaway point all happening at the same place. So let me draw with color. It might be helpful to think about it that way. I've got a pole that's doing something like that. I've got a pole that's doing something like that. And then I finally have the third pole that's coming through and doing that. That's one way of thinking about it, but that's what the root locus actually looks like in this case. It's a very unusual kind of root locus. We would not have known about it if we hadn't solved and known that at minus 3 I've got something special going on. Then finally, when A equals 50, we have again that the two roots go straight up and straight down there. Notice that the 0 is so scrunched in just because of the scale we have to have. And we have a breakaway or a multiple point at minus 2, which is somewhere around there, and minus 24, which is right about there. And sketching this in, I've got one root which does something like that, another root which does something like that. One of them goes toward that 0, the other one goes this way. And then I've got this root here which is coming across. They intersect and one goes up and the other one goes down. Very interesting behaviors, the same, very, very similar system. I just have chosen different values at that pole location and get quite different root locus plots when I do that. If you wanted to verify your answers, I really want you to know how to do this by hand, and exams and so forth, you'll have to do it by hand. But it can be really handy to check your results. And MATLAB in the Control Systems Toolbox, which we have on the campus computers, is able to do that. So suppose I have a transfer function g of s is some numerator divided by denominator. I can enter in the numerator, think about it as this rational polynomial, and I can enter the numerator coefficients into a vector and the denominator coefficients into a vector. MATLAB makes no restriction that this be a monic polynomial. It can handle the more general case where we have a general polynomial where these coefficients are not 1. And you simply type in r locus b comma a, and it plots the root locus plot for you. Also, if you want to know what value of k gives you a point on the root locus, you do k equals r log find b comma a, and it will bring up the root locus, and you can click on that locus with the mouse, and it will give you the value of k for a specific point on the root locus. That's also extremely helpful. Lastly, some extensions. And we've looked only at systems that are in rational polynomial form. We haven't looked at anything different from that, and there certainly do exist transfer functions in many other different forms, but rational polynomial is usually sufficient for control system designers. But sometimes we have actual delays in the system, some transport delay. And when we have a transport delay, we have the plant has this e to the minus tau ds times some rational polynomial transfer function g prime of s. And prime doesn't mean derivative or anything, it just means some other g. But the offending term is this exponential, which says that if I have an input to the system at time 0, like a step or an impulse or something, then nothing at all happens in the output until time tau d, and then it starts doing whatever it does. There's actually a transportation delay of tau d between the input signal and any impact whatsoever observable at the output. This is not a rational polynomial transfer function form. That e to the minus tau ds is something quite different. So bottom line, we cannot use the root locus techniques that we have developed directly, even though a root locus plot does exist. We do have 1 plus k times g of s equals 0, but solving for where that locus is made much more complicated because of this e to the minus tau ds that we'd have to consider as well. There's two methods that people use to at least approximate what this will look like. And one is, well, if it isn't a polynomial, let's approximate it by a polynomial that looks a lot like it. And so let's say e to the minus tau ds, the offending term, looks like or could look like some b0s plus b1 divided by a0s plus 1 for some intelligent choice of the b0, b1, a0, and so forth. So what it can be done is what's called a Pade approximation, where e to the minus tau ds is approximated by 1 minus tau ds over 2 divided by 1 plus tau ds over 2. This is a first order approximation. There's a second order approximation that's given there also, which is a little bit better, and something that's even a little bit simpler than either of those, but very, very crude in its approximation. But basically you can think of this as something like a Taylor series expansion of e to the minus tau ds, although with a numerator and denominator, not simply an infinite series polynomial by itself. That's one idea for how to deal with transport lag, with delay in a system. This is extremely important for digital control, as it turns out. We're going to study digital implementation right at the end of this course, not getting into digital control design, but how do I do a digital implementation of an analog controller. And the biggest issue that we will find is that the digital system will hold the output signal going into the plant for the sample period using its digital to analog converter. And this hold, if I compare the signal that it's holding, which is going through the leading edge, the leading edge of these things, and what it kind of sort of looks like average, the average signal looks kind of like a delayed version of that. And so using this a root locus with a delay in it will help us understand what the actual controlled system will look like better than if I don't include the delay. Another approach, which is exact but harder, is to directly plot the root locus using the phase condition. So that is, the angle of g of s, which has to equal minus 180 degrees to be on the root locus, is going to be equal to minus tau d omega from the first part, from the exponential part, plus the angle of g prime of s, which is the polynomial part, if s is sigma plus j omega. So the omega term, the imaginary part, comes in there. So one approach would be to plot the root locus for this, the thing that we know how to plot, and then search horizontally, so fix some value of omega for that S, and then search horizontally nearby that locus for where this locus condition is satisfied. So we want the angle of G prime of S then to be 180 plus tau d omega plus 360 L. Or alternately, we have to find the value of omega for which that's true. So in any case, we can work with delays. I'm not going to go into that more in this course, but it is a significant concern in some cases like digital control system design. And finally, we have assumed that k is between 0 and infinity, and that g of s has monic numerator and denominator transfer functions. So if either we're interested in what happens when k is negative, or if a or b have a negative sign preceding it, then we have to change our root locus plotting rules to handle that case. And the changes are not major, we just have to remember to do it. So the root locus plotting rule is still 1 plus k g of s equals 0, or g of s is minus 1 over k. But we have to think about what happens if k is negative. The magnitude condition doesn't change, but the angle condition does. If k is negative, I have to look for locations in the S-plane where the angle of g of s is 0 degrees instead of 180 degrees, and that changes a few of the steps. So I have included here a summary of what happens if k is negative, or if I'm plotting a 0-degree root locus. Step 1 is the same. Plot all the poles in zeros. Step 2 is different. The real axis rule is going to say the locus is on the real axis to the left of an even number of real poles and zeros instead of an odd number. So the angle criteria changes that slightly. The asymptote condition changes slightly as well. No, it doesn't. If you compare very carefully what we have here to what we had before, you'll notice n minus m is number of asymptotes. That's the same. The alpha is the same, but the angles are different, and so you have to keep that in mind. If you're looking at the departure angles, again, there's a slight difference there. There's no minus 180 degrees in here, so that's slightly different. Step 5 is the same. That's the Routh test. Step 6 is the same. That's the breakaway points. Step 7 is the same. Step 8 is the same. So the only steps that have changed are ones that I have highlighted here. Step 2, italic boldface. Step 3, italic boldface. And step 4, italic boldface. Those are the only three, and they're very, very minor changes, so you should be able to handle either case. So that concludes our section on root locus analysis. With a little bit of practice, you should be able to plot very, very complicated root locus plots using either the 180-degree rules or the 0-degree rules. You should be able to find the real axis part. You should be able to find the number of asymptotes and the angles of the asymptotes. You should be able to find arrival angles and departure angles. You should be able to find places where the root locus plots intersect. You should be able to find where they cross the imaginary axis and for what value of k. And when you have a root locus plot and you have a desired point S0 through which the locus passes, you should be able to find the value of k that puts the poles at that point. So that concludes our chapter on root locus analysis. From here, we're going to go into a chapter that leverages all of this information and is thinking about root locus design. How can I design a controller to meet the transient response specifications we talked about earlier using ideas that we garnered from the root locus plots?